Hey guys, this is problem 2 for tutorial 3. The first one was pretty long, so I'm just gonna, but it was okay because I only want to cover one thing here. I think the thing that's going to give you guys the most trouble is this applied moment, m equals 5pl. And I'm just going to explain how applied moments affect your solution. You're used to seeing applied loads, applied point loads, P, and if you remember correctly, those things directly affect your shear diagram graph. They do not. The point loads can cause discontinuities within your shear diagram. Your applied moments cause discontinuities in your moment diagram. And here I'm just going to give you guys a brief example. When you're doing analysis when you're trying to find the reactions for this, it's just like any other problem. You still use your same equations. A moment about a point, and these still equal 0. But some interesting things happen. If we look at this case where we have no forces in the x direction, no forces in the y direction, just this applied moment, and we'll call this L, your ax is going to be 0. Your ay plus by will equal to 0. And your moment about, let's take the moment about A, the sum of your moments will be equal to 0. And let's calculate this very quickly. If we do this clockwise positive, we end up having that negative 2pl minus bl equals 0. Then our bl equals negative 2pl, and our b equals negative 2p. And notice that this reaction is not 0. We do have, this moment does cause reactions. And the reason why your diagram, or the way you calculate the other forces is that, like, how to say it? It's kind of hard to explain, but you're not, I don't think you're used to seeing reactions develop without loads. Okay, so we have that, and then from sum of forces about y, we'll do ay equals negative by equals 2p. Okay, now remember that your moments can always be broken down, broken into a force couple. So this moment is equal to two forces that are separated by L, and we'll call this 2p. We'll call this 2p. This gives you your moment. And having two of these together means that you have no net force. You have pure rotation. Okay, now that we have this, let's draw the shear and moment diagram very quickly for our thing. I believe that I have axial force is red and shear force is green and moment is blue. So right away you know that your axial forces are equal to 0. There are no axial forces. Your shear, however, is not equal to 0. Even though you have no point loads, even though you have no distributed loads, this moment causes a shear. And let's see what happens here. Well, first I need to let me draw this over here and redraw the diagram. You have no force, A equals 0. Your axial force, your shear, is just going to be 2p. Because it's just here. Your shear goes up by 2p at A and goes down by -2, or goes down by 2p at B. Your moment, and this is probably where it's going to be the most interesting. We have this way positive. So your sorry, I should have written the equations down. Your v of x is equal to 2p, and it's just constant. Your m of x is equal to 2px, where this is your x direction. So you go like this. So this length here is equal to 2pl. This is pl, and this is pl. So I guess you can see you can have your moment diagram. You don't need to worry too much about your moments. Just treat everything like you've been treating it before, and then whenever you see this, just remember that it enters your moment equations only. Or it only enters your moment equations. It does not enter your forces. The reason it appears in your shear force when you calculate your reactions. So when you get your reactions, the reactions will take this m into account, and you don't need to worry about what kind of effect it has later until you're drawing your shear diagram. You'll notice that like any concentrated load, this requires us to use two equations. I kind of cheated here. This is only for x less than L. For x greater than L, L over 2, you have m of x equals 2px minus 2pl, and these are the equations that you'll need for your thing. There was one last thing I was. Oh yeah, note that the position of this does not matter. You do not have an extra length factor. This entire thing here is your moment. This is m. You have normally you have like p times l to get your sum of moments, but the location of the moment does not matter when you're working with concentrated moments and you're trying to use sum of moment equation. So yeah, let us know if you have any questions with this. Let me bring back this diagram. I'll just note one thing very quickly. Even though this ends at a pin, and even though even though this ends at a pin, this applied moment here means that your shear moment diagram will not end at 0. Your moment diagram is going to look something like this. You're going to have something here, and then it's going to go like this, and it's going to go back up. And this is going to be 5 PL, kilonewton meters. Okay. Yeah, let us know if you have any questions.